Hi, this is Dr. Emenacker. In this video, we are going to take a look at some examples of differential equations. What I want you to see is that differential equations isn't just something that was invented to torment people, but it has applications in the real world. And then after we've looked at 7 examples, I want to go back through each of the equations and look at how are they classified. As we move through this course, it's going to be very important for you to be able to identify what class an equation is, because the classification will determine the strategy or strategies that can be used to solve that equation. So this is some very important ideas. Recall if your head starts to get through partway through, you can always pause and take a break and come back to it. Okay, so let's start out with something pretty straightforward here. Example number 1, we have that y prime equals x. Now, we are used to seeing, or you are used to seeing things like y equals x or y equals x squared. Okay, those are no big surprise to you. But here we don't have y equal to, we have the derivative is equal to x. And what we need to do is we kind of need to think backwards. The question here is, if the derivative is x, what was the original function? Well, to undo a derivative, as you'll remember from your Calc 1, you integrate. So what I'm going to do is I'm going to integrate both sides of this equation, and it'll give me the integral of y prime is equal to the integral of x dx. I'm being a little bit casual here with my integration notation, I realize that. But what winds up happening on the left side is that when you integrate the derivative of y, you get back y. On the right-hand side, when you integrate x, you get 1/2 x squared plus c. So in this first case, we start out with a very straightforward differential equation, y prime equals x, and it's fairly straightforward to solve. Y is equal to 1/2 x squared plus c. We're not going to solve all 7 of them, but we want to take a look at various differential equations, what the forms can look like. A second situation that we can run into is something like what's now at the top of the screen, where we have y prime is equal to 2 times y. Now, what this is essentially saying is that when I take the derivative of y, I get back y, the original function. We'll talk about that in a minute. In this particular problem, we're also given some additional information. We're given what is referred to as an initial condition. This is something that you saw in Calc 2 and Calc 3 where you integrate and you get your constant of integration, your plus c, and you can solve for the value of c based on being given an additional piece of information. So here we're given an additional piece of information. We're told that the value of y is equal to 7 when the x value is 0. Well, as you think back through all of your calculus adventures, you recall that the derivative of e to the x is e to the x. In other words, if we take the derivative of the function, we get back what we started with, which is essentially what this equation is saying. When we take the derivative of y, we get back y plus a little change, a little extra, that coefficient of 2. But essentially it's saying we get back the equation we started with. The solution to this is based on realizing that the derivative of e to the x is e to the x. So we can write down that y is equal to our e to the 2x, the original equation we started with, okay? Realizing that this 2 here came from taking the derivative of e to the 2x, and we're going to include a constant out front. This constant out front is going to allow us to adjust our equation, moving it from a general solution, which is what we have right now with y equals c e to the 2x, taking our initial condition, substituting in 0 for x and 7 for y, we now have 7 is equal to c e raised to the 2 times 0. Well, that's e to the 0, and e to the 0 is 1, which then gives us that c has a value of 7. We can substitute this value of 7 in for c in our general solution. When we do that, as you can see over on the far right-hand side, we now have y is equal to 7 e to the 2x. This is a particular solution, particular because the coefficient in front is adjusted to a specific initial condition. Okay, when we are looking at differential equations, we do not have to stick just with y prime. We can look at second order derivatives, third order derivatives, first, second, third derivatives, things like that. As you can see with example 3 now at the top of the screen, we have the second derivative of y is equal to g. Okay, if we want to solve for y, we integrate both sides. Now, this time I'm just going to use the variable t is my variable. G is just some number. Could be a gravitational constant, could be who knows what. Okay, so what this is actually representing here is, if you think back, the second derivative refers to acceleration. The first derivative refers to velocity, and the function itself refers to the position of whatever the item is that you're interested in. So what we have right now is acceleration is equal to the gravitational constant. If I integrate each side, my second derivative will go from being a second derivative to a first derivative. On the right-hand side, g is just a number, like 9.8 meters per second squared. If I integrate with respect to the variable t, I'm going to get g times t plus an integration constant. Okay, this is our velocity equation. If I take the velocity equation and I integrate that, I'll get the position equation, which on the left-hand side is just going to be y. When you take and integrate the derivative, you get back what you started with, in this case, y. On the right-hand side, when I integrate, I'm going to get a t squared. I'm going to have to divide by the 2, so I'll get g over 2 t squared, c times t, plus I'll have a second integration constant, d. Now, there are a couple things I want you to notice in this example. First, if we want to solve for c and d, we need two pieces of initial information. We need a piece of information to allow us to solve this equation for c. Once we've solved for c in this equation, we can then take that value, substitute it here, and use a second piece of information to solve for the constant d. In general, okay, and this is important here on the right-hand side. In general, if you have an nth derivative, also referred to as an nth order equation, you need n pieces of information to compute a particular solution. So if this was the fourth derivative, for example, we would need to have 4 pieces of information. An example of one such piece of information could be y of 0 equals 40. Y of 1 equals, no, I'm just making up something, 86. In order to solve this particular differential equation to get a particular solution, with these 2 pieces of initial condition or information, we could actually solve now for the constants c and d and come up with a particular solution. Keep in mind this information here in the box to the right, in the yellow box. If you have an nth order equation, you need n pieces of information to get a particular solution. This is important. Don't let that just slip by in this video unnoticed. Okay, so let's get into something else. We've just started with 2 very straightforward differential equations. We moved to a differential equation involving a gravitational acceleration. Let's move into something with a simple spring. Okay, we have here a situation where we have a spring mounted to a board or something or other, the ceiling. It's hanging down. Attached to the other end of the spring is a mass. And coming off the bottom of our mass is a plunger or something like that that goes into a container with some type of a fluid. Now, what's happening with this container in the fluid is it acts as a damping force. If you just had a mass on the end of a spring and you pulled it down and let go, the thing would boing up and down and up and down and up and down, and it would take it a while to settle back in and stop moving. With this plunger submerged in some type of a fluid, it's going to slow down the response or the recoil. Okay, so the thing's not going to bounce around a whole lot. It's going to move and then come back to its original position. On your car, you have shock absorbers or struts. They both do the same thing. The idea is the car's riding on a spring of some sort. When it hits a bump, the spring compresses and the spring pushes back down, and left to its own devices, it would bounce back and forth for a while before it settled in. This would be a problem with your tires bouncing around for the next tenth of a mile while it finally settles back in. So what the shock absorber does is it slows down um, this response so that things settle back in very quickly. Okay, well, let's take a look at this and see if we can come up with an equation that describes how this system responds. First thing to remember is force is equal to mass times acceleration. Probably familiar from early physics with that. And another very important thing to remember and keep in mind throughout this course is that acceleration is the second derivative. We saw that back up in example 3, the one just prior to this. All right, so if we take our force equals mass times acceleration over here on the left-hand side, we can rewrite this as mass times y prime. Now, where did y prime come from? If you take a look in red here, y represents the displacement. How far is the spring stretched by the mass? Well, displacement, if you'll recall, going back up to example 3, up in the upper right corner, displacement is the change in position. That's y. So this displacement, this force that we're looking at is y. We want an acceleration. Well, the acceleration is the second derivative of y, which we also saw in example 3. So we can ultimately rewrite mass times acceleration as mass times the second derivative of y. Okay, so we have that. Where do we go from here? First thing we need to realize is that part of our system is going to be the behavior contributed by the spring. Hooke's law describes how that behaves, where essentially the displacement is equal to, or the force is equal to the displacement, the amount that the spring has moved, times the mass. We can see that in this first part of the right-hand side of our equation. K is going to be our spring constant, and y is the displacement. Y, going back to example 3, with the change in position. The change in position is just how far is the spring stretched when the mass is hung on that spring. Then what we're going to have happening here is we're also going to be losing some energy through the damping force. The damping force is going to be right here. Okay, there's our damping force. It's this part. And what's going to happen is we're going to have a couple things going on. The damping force is going to be taking movement out of the system. It's going to be taking acceleration out of the system. So we're going to have some type of a damping coefficient here times the velocity. How fast is the thing moving? Oh yeah, that is the first derivative right there. Okay, so we have this being taken away from the system, which is why it's subtracted. And the very last thing that we have is we have some force being added to the system, which is right there. All right, that's all the further I'm going to go with this one. I want you to see where this equation comes from. We're not going to solve this right now. We don't have the technique in place just yet. We'll get to it as the semester goes on. But what I want you to see is you can come up with an equation like this. And what I'm ultimately going to do is I'm going to rewrite this so that we wind up with my double prime plus k well, let me put the cy prime first. So I have my derivatives in order, plus ky equals f of t. Now what I've done is on the left-hand side, I've moved all of my terms that involve y or a derivative of y. And on the right-hand side, I've just left the function that's only in terms of my variable t. So there's that one. This isn't an equation or a class of equations that we're going to spend some time looking at how you solve. Another example involves a pendulum. You start with a weight on the end of a string or something or other. You move it over some amount. And then when you release it, it's going to want to move back to its original position. There's a force, gravity, acting down on this mass, trying to move it back to its original position. Okay. The force, in part, depends on the weight. Now, remember, weight is the mass of the um, pendulum times gravity. So we can move from weight to mass by multiplying by the gravitational constant. Okay, if I take a little more careful look at this, I'm going to redraw this, and what we're going to have here is a situation where we've moved the pendulum over some amount that we're going to call y. So that's a measure of our angle. And we're going to have our force acting downward is going to be mass times the gravitational constant times the sine of the angle. So that's going to be the sine of y. If we take this, this is going to be our force moving in a downward direction. So what we're going to have now is that the length of the pendulum times its mass times acceleration, oh yeah, that's this y prime, is going to be equal to the negative, why the negative? Because the pendulum's going to want to move left, times mass times gravity times the sine of y. In this case, it gives us the equation that we have down here. In this equation, notice both terms do have a common factor of m in them. We know the mass is not going to be 0, so it's okay to go ahead and divide by that constant, and it gives us this equation here. So we wind up with this as the equation we're going to be working with, trying to solve. Okay, let's move on to another one. Fortunately, COVID is hopefully in the rearview mirror and we're done with it. But one model of how an epidemic spreads, and this is not a real accurate one, okay, you can get much better ones, but just as an illustration of a simple differential equation, we'll go with it. Let's say that we have y is equal to the fraction of a population that's contracted whatever the disease is. If y fraction of the population, so if a fourth of the population is sick, that would mean that 3/4 of the population is not sick, 3/4 coming from the whole population minus the sick part. The whole population's 1 minus the sick part. So there we have the fraction of the population that's sick is y. The fraction of the population that's well is 1 minus y. And if the question is, how quickly is this spreading? How quickly it is spreading is really asking how fast is the fraction of the population that is sick increasing. That's y prime. That's this right here. So we could write this as y prime equals dy dt. In this case, I just used dy dt to remind you that either notation will work and to get you used to seeing both notations so you're not taken back if you see one or the other. Basically, a simple model of how fast it is spreading is going to be a coefficient that deals with how readily it spreads from one person to another times the number of contacts between well and sick people. If you take and you distribute the alpha and the y, you get alpha y minus alpha y squared, which gives us then the equation over here to the far right, y prime is equal to alpha y minus alpha y squared. Once again, it is a differential equation because it involves a derivative. That's something that will be the case with every single equation we encounter. It will have a derivative, a second derivative, things of that nature in with it. Let's take a look at one more example. This one's a little more lengthy. You've got some kind of a fluid. Okay, it might be something more viscous like glycerin. It might be something less viscous like isopropyl alcohol, or something kind of in the middle like water. Who knows? But what you're going to do is you take a plastic bead. Now, I'm not going to identify a specific type of plastic because they vary in their densities. But the point is you drop this bead in the fluid. If the fluid is not very viscous, the bead is going to fall fairly quickly to the bottom of the container. If the fluid is fairly thick, molasses, and you drop the bead in, the bead is either going to sink much more slowly than in like isopropyl alcohol, or the bead might not even sink at all. It depends on the density of the bead compared to the density of the fluid. And we'll see this here. Okay, there are several forces that we're going to need to identify here. On the far left, buoyancy, B, is the tendency of that bead to want to float. That buoyancy essentially talks about the amount of fluid, the mass of the fluid that you have to displace to get the bead to move. There is a resistance between the bead and the fluid, just like when you move through the air, there's air resistance. We'll call that R. And then you've got the weight of this bead pulling it downward. We'll call that W. Now, we're going to call the radius of the bead A. So A is going to be the radius of this bead. Rho is going to be the density of the fluid, okay? And then bar rho is going to be the density of the bead. Real important to notice that the density of the bead must be greater than the density of the fluid. Notice I've put this down over here. Why is that the case? You may want to pause the video and give this some thought. Why does the density of the bead need to be higher or greater than the density of the fluid to get this situation we're looking at? Well, hopefully you've come up with an answer, or at least an idea. And the reason it has to be greater is if the density of the bead is less, it's going to float. It's not going to sink at all. Okay, so let's start with a basic formula. We're interested in how fast is this thing going to fall? Okay, well, we start off with our good old equation, force equals mass times acceleration. Notice what I'm doing here. I'm rewriting my mass times acceleration as mass times v with a dot over it. That dot over the v means the derivative of v. And as we talked about back in the third example, the derivative of velocity is acceleration. So all I've done is I've rewritten the force equation to involve the derivative of velocity to replace the acceleration. Now, the force, okay, is going to be, let's take a look at the forces that are acting. The force in a downward direction is going to be the weight of the bead. One of the forces acting in an upward direction is going to be the resistance between the bead and the fluid. And another force acting to push the bead upward is going to be the buoyancy. So what we have here is our force, which is mv prime, is equal to the weight minus the resistance minus the buoyancy. Well, let's go after this. First thing we're going to do is we're going to take a look at how do we compute the mass. Well, mass is just density times volume, which essentially is what we have here. The 4/3 pi times a cubed, remember a is the radius, is the volume of the bead, and then multiply it by rho bar is the density. So there's the mass of the bead. The weight, okay, aha, yeah, weight, that's not mass. The weight is going to be the mass of this bead times g, the acceleration constant due to gravity. So now we have a weight there. The buoyancy is going to be the amount of fluid, okay, the mass of the amount of fluid that the pearl displaces. So what we're going to wind up with is the volume of the pearl, which is going to be our 4/3 pi a cubed, times not the density of the pearl, but remember it's displacing a fluid, so it's going to be the density of the fluid that it's displacing. Buoyancy is essentially measured as the amount of fluid that you're displacing. That's the amount of resistance that's offered to keep this thing from sinking. Okay, so we can now run and use Stokes' law, which says that R, what's R again? Okay, oh yeah, R is the resistance that's measured between the bead and the fluid. Okay, so what's going to wind up happening here, Stokes' law says that the resistance is going to be a coefficient of viscosity, okay, or mu, times A, which is the radius of the bead, times V, which is the velocity. Remember, as you move faster, there's more resistance. Okay. For example, when a spaceship or whatever, I was going to say the shuttle, but they just haven't used that in quite a time. When something's coming back into Earth's gravitational field, back into the atmosphere, actually, the faster it's moving, the more the resistance, and that resistance causes heat. As the thing slows down, there's not as much heat generated. That's why you running through the rain or running from one class to another don't turn red like the space shuttle coming back in would. Okay, so it's definitely dependent on the velocity of the item as well. Okay, we've got a variety of pieces of information here, and we want to substitute this information into our equation up here in the yellow box, m times v prime. This is actually a differential equation, remember, because v prime is the derivative of v. So let's start putting things together here. On the left-hand side, remember the mass is this. It's the volume of the bead times the density of the material from which the bead is made. So there's that. Now what I'm going to do is I'm going to move the resistance to the left-hand side. And the reason for that is just because I want to get all of my terms that involve V or some derivative of V on one side and the terms that do not involve V on the other side. So I'm just setting it up to be in a form that's more reasonable for a differential equation. Okay, so I'm going to move the resistance to the left-hand side. Recall from Stokes, here is our mu AV. Then the, I want to say ballast, okay, our buoyancy winds up being this right here. And we have one thing that's kind of buried in the middle that I've overlooked here, which is the weight. The weight is going to be this term right here. So we have our mass times the derivative of velocity plus the resistance is equal to the weight minus the buoyancy. The reason the weight and the buoyancy are on the right-hand side, just to remind you, is because they do not have v, v prime, or any derivative of v in them. I'm trying to isolate the v terms from everything else. Now that we've done that, I'm going to take this equation right here, and as we start to work with these differential equations, I really want the coefficient on my derivative, this term right here, I want that coefficient to be a 1. So for that to be a 1, I'm going to divide by the 4/3 pi r cubed times the density, that is not going to be 0 because what we have is the volume of the bead times its density. So it's okay to divide by it. We're not going to get a divide by 0 situation. When I divide by that coefficient, I have v prime plus, and I'll leave the algebra to you, but it's going to be 3 mu over 4 pi. One of the a's cancels, and we have a squared rho bar v minus or equals, and then on the right hand side, lots of stuff cancels out, and we just have g minus rho over rho bar times g. Okay, so this gives us a differential equation. Differential because it involves a derivative. Now, at the start of this video, I mentioned that being able to classify these equations is very important. There are two elements we're going to focus on in classifying these. One of those elements is going to be the order. The order references what power derivative do we have as the highest derivative in that equation. In the first equation, our highest derivative was a first derivative. So that would make it a first order equation. In the second example we were given, we had a first derivative. So that's going to be a first order equation. In this third equation, we had the second derivative of y, which makes it a second order equation. And I'm sure you can follow down through the rest of these. Here, the highest derivative is 2, second order equation. Here, the highest derivative is 2, second order equation. Example 6 is a first order derivative. And then example 7, remember that means a first derivative, is a first order derivative. So there are two things we want to look at. One, what is the order of the equation? Got that, hopefully. The second thing we need to look at is this equation linear or non-linear? In the first example, notice our x has an exponent of 1. That's linear. Okay. If it would have been x squared, that would have been non-linear. But since it's just x, that's a linear function. In our second example, we don't have anything squared or cubed or anything of that nature, so it qualifies as linear. The third example, for the same reason, not having a square or anything like that, is linear. Now in this fourth one, people are thinking, man, there's a lot of activity there. That's true, but the exponent on everything is a 1. We don't have any y squares or anything like that. So this one is going to be linear. As we move to example 5, notice that we have this sine of y. Sine is definitely not a linear function. So this is going to be second order because it's a second order derivative, and it's going to be non-linear because we have sine applied to our y. In example 6, you'll notice that we have a y squared. Boom, that disqualifies it from being linear. This is a non-linear equation. Now, something to notice is the order and linear or non-linear are not connected to one another. They are independent of one another. You can be second order and non-linear. Okay. You can be first order and non-linear. You can be second order and linear. So don't go looking for some pattern and say, aha, if it's second order, it's non-linear. Well, that's not true. Here's a counterexample right there. In our last example that we were provided in this video, we talked about being first order. Now, looking at v prime and v, neither of them is squared or cubed or the sine of it or anything like that. They're just an exponent of 1, which makes it linear. Being able to classify these equations is very important, as we talked about earlier. Okay, and I know I've mentioned it earlier. I'm trying to emphasize the fact that it is very important for you to be able to identify what type of an equation you have, because it will determine the technique that you use to solve it.